and thank you for organizing the cycling research group and these meetings. It's really fantastic that we can all share our knowledge and start to interact in this way, which I think has long been overdue. So I'm going to be chatting this morning about kinematics in cycling, and this is a field where we've been quite active in research in the last decade. And so it's great to be able to collate a lot of other research with ours and try and put things into context. So when we talk about kinematics, sorry, I'm just going to quickly get hold of for some reason I'm not able to advance my slides. Oh, there we go. Now I can. So when we talk about kinematics, we're talking about the motion of either points or objects or systems of objects and points without specifically talking about the forces that cause them. So what we're talking about in this discussion today is really just about the movements and the position of various different objects and points without trying to understand specifically how they interact and how they may be affected by various different aspects relating to cycling. That's a much bigger talk that may take a lot more time. I see if people are being admitted, I can't advance my slides. I'm just quickly closing that, and I don't know why the system does that. There we go. All right, so in cycling for already since the early days and probably going back into the 20s or 30s, the 1920s or 30s, I guess, being over 100 years ago, static kinematics have been used from that point on in various different ways. It's only really in the last 20 years that dynamic kinematics in 2D kinematics and more recently 3D kinematics have become used on an everyday basis in cycling. And so it's important for us to understand what we're actually measuring and how we're measuring kinematics using these different tools. And so it's very important, and this is something I emphasize in many of my talks, to know your tools, know what you're using, what the limitations of those tools are, what the accuracy of those tools are, and whether or not they're valid before you actually make any inferences about what you're doing with those. And so if we look at the goniometer, the humble goniometer, you can call it, this has been used, and we've been using the goniometer in our lab and collecting data on all joints in cycling right since 2003. So we're talking almost 2 decades worth of data, and we have probably a data set of excess of 4,500 to 5,000 individuals on not just knee flexion angle, but the other important joints, because the body is not just the knee. We're talking about the hip joint, the shoulder joint, the elbow, ankle, and other joints. And that has given us quite a good understanding of these joints when measuring with a goniometer. About 5 years ago, we switched to an inclinometer, and thank you to Wendy Holliday, who's in the audience today. Dr. Wendy Holliday needed a different tool to the goniometer for anatomical reasons, and we developed this inclinometer with an extension and started measuring using the inclinometer and have been doing so ever since. 2D kinematics is easily available. There is free software available. You can pay for software, but they are all very functional software systems and are used by many fitters and many labs around the world. And then we have really high quality 3D kinematic systems, such as we use in our research laboratory, the Vicon system, which uses 45 markers. So it's an extremely sensitive system to all planes of movement and is used in research, but is not an easy system to use in everyday practice, and also not an affordable system, and certainly not affordable by bike fit practitioners. If we look at the accuracy of 3D kinematic systems and we look at the literature, we get these sorts of results where the accuracy is purported to be within less than 1/10 of a millimeter in terms of differentiating between points. So that is an extremely high level of accuracy. And if we look at commercially available systems that are used by bike fitters, such as the OptiTrack system, which is used by a number of different software packages and fitting systems, we see a similar level of resolution where the differentiation between different points is down to 0.2 of a millimeter. a very high level of accuracy for that equipment. And that's led to people having the understanding that these systems are the most accurate way of measuring kinematics. And because the person is actively pedaling, the most valid way of measuring cycling kinematics. And the question is that really the case? And do we understand that well enough? Well, what you're referring to in those last two papers are the instrument error. And within subject variation, or what we could refer your typical error of measurement, it's a combination of the technical factors relating to the instrument error and then the human being measured. And humans have a much higher rate of variation because we are not machines. And there in that area, marker placement is a source of error. Finding the anatomical landmarks and reproducing them is difficult. When the subject starts to move, the markers are placed on clothing and on skin, and the clothing moves over the skin and the skin moves over the underlying structures. And so you have marker movement and displacement of those markers. And then every time you measure a human being, we may move in different ways. In fact, that's well validated from research in that we have very variable movement patterns, and that's a sign of good health. But that means that the movement that you measure may not be the same as the movement you measured a week ago or a day ago or a month ago. And so combining all of those factors, and in fact, that paper I presented in the previous slide, this is actually a quote from the abstract: the uncertainty of marker placement relative to underlying skeletal features and soft tissue artifacts produce errors that are orders of magnitude larger than the errors attributed to the camera system itself. So how big are those errors? Well, Wendy, as part of her PhD, her first study was looking at the typical error of measurement between goniometer, the inclinometer, which we're using, and then Vicon 3D kinematics. So the gold standard, I guess, in 3D kinematics. And if you look at the error, you can see that for the goniometer, a minimum error of 2.7 degrees and a maximum of 4.1. For an inclinometer, 2.6 and a maximum of 4.5. And they vary depending on the joint. And for 3D kinematics, a minimum of 3.1 and a maximum of 4.8. So not actually a lower typical error of measurement for 3D kinematics compared to a goniometer and an inclinometer. In fact, slightly higher, but all within a very similar range. And in fact, this is a very low typical error of measurement for any instrument where we're measuring kinematics. And so each of these three tools is equally accurate and reliable. The question then is, are they valid? Well, if we look at the results of that study, we see that for the different joints, the knee, the hip, the shoulder, and the ankle, we get different means for the same subjects on the same day over a period of 3 weeks. So each of them is measuring these in a different way and coming out with a different result. Well, which one is right? If we look at the hip, we see 70, 77, and 87 degrees, 7 and 10 degree differences, which are quite significant differences. And we see that similarly for the shoulder, and we see that as well for the ankle joint. Why is that the case? Is one more valid than the other? Well, they measure things in a different way. If we look at the goniometer, okay, and this may seem crude, but it's very reliable. Looking at the angle subtended by the sacrum versus the long axis of the femur and measuring that angle of the goniometer versus a Vicon, which uses markers on the anterior superior iliac spine, the posterior superior iliac spine on both left and right, and therefore makes a quadrant out of these and takes a perpendicular axis to this and then looks at the relationship between that angle and the long axis of the markers on the thigh, and then measures the hip flexion angle. So here we're looking at hip flexion angle. They are both measuring the same thing, but they are measuring them in different ways. And therefore, the results differ, even if they are both valid. The shoulder is one that's a little bit more difficult. The shoulder is a joint that is complicated by the fact that it moves in many planes at the same time and also has two different components, the scapulothoracic part and the glenohumeral part, and they all move at the same time in different planes. And that makes it very difficult to understand exactly where in a particular range of motion it is. The Vicon tries to differentiate those by taking all planes of motion into account. But when you use an inclinometer or a goniometer, you're really only taking the sagittal plane into account. Whereas 3D kinematics, as particularly this marker over the humeral head starts to internally rotate, it displaces that axis and therefore comes up with a different measurement. And this is actually still a confounding issue, which I'll get to later on in my talk when it comes to measuring shoulder flexion angles. The ankle is quite straightforward with the inclinometer measured through the lateral malleolus and the fifth metatarsal head versus Vicon, which uses a marker on the top of the shoe and the heel, which are in the same plane, and the ankle. And if you look at commercial systems like STT, using markers that triangulate various different anatomical points. But they are all accurate and reliable. They just measure and valid, but they measure these points in a different way. So let's start with the knee, and we look at knee flexion angles and what those measurements actually mean. Well, for many years, the knee joint has been measured at bottom dead center since Andy Pruitt and Holmes published their book, Lower Extremity Overuse in Bicycling in 1994, and promoted this technique named after Holmes. Bike fitters have used this technique to set saddle height optimally, and that is by placing the crank at the bottom dead center position, putting the pedal in a horizontal position. That's an important aspect. If you don't place the pedal in a horizontal position, it is not the Holmes technique and it's measuring a different angle. And then measuring the knee flexion angle through the greater trochanter, the lateral femoral condyle, and the lateral ankle malleolus. And in fact, here is Andy Pruitt, who's up until recently was still actively involved in bike fitting and has contributed greatly to our understanding of bike fitting using the Holmes technique to set saddle height. And if we look at the research, Will Peveler's research, where he looked at oxygen cost related to different angles in this using this Holmes technique and power output. And if we look at Rodrigo's own research on bicycle saddle height and knee injury risk, we see that having a Holmes knee flexion angle of somewhere between 25 and 30 degrees improves economy, reduces perceived exertion, improves power, and reduces injury risk. And for that reason, we have a recommended range of 25 to 35 degrees. The 30 to 35 degree range is there because some individuals may not be able to reach 25 to 30 degrees due to various factors such as hamstring flexibility and neuromuscular reasons. And so there's a wider range than is purported by the optimal in terms of injury reduction and performance. But that's been used by bike fitters for a long time, including ourselves, and so is clearly validated by the research. But many bike fitters and researchers would say, well, the person isn't actively pedaling, so this is not a valid measure of what actually happens on the bike. So what actually happens if we look at, and this is in Rodrigo's PhD thesis. Rodrigo can maybe tell us afterwards if this has been published somewhere because we can't find it, but in his thesis itself, the chapter looking at the change from static, so using the Holmes method, to dynamic at a workload which was not clearly specified. It's basically comfortable intensity, simulating riding down a flat road, if I recall correctly. And what we see is at the bottom dead center position, knee flexion angle changes from 30, so right in smack bang in the middle of that Holmes range, to a knee flexion angle of 38 degrees. So about an 8-degree increase in knee flexion angle. And at the same time, and it's important that I incorporate it here because it relates to this, is the ankle plantar flexion. And that increases by similarly 8 degrees. If we look at Will Peveler's study from the Journal of Strength and Conditioning Research, similar findings, and here is stationary, okay? This is level 1. Level 1 was defined as 1 kilopond. I actually had to go and look it up because a kilopond is basically a 9.8 Newton meters. So in other words, the force of gravity, God knows where they actually still use that, maybe somewhere in the States where they're not metric yet. But anyway, that's level 1, low intensity, in other words. And then at an intensity equating to a respiratory exchange ratio of 1, and then a maximal intensity. And what we see if we look at the knee and ankle kinematics is that at stationary, to level 1, we see an almost identical change to Rodrigo's study of 8 degrees of increase in knee flexion, and similarly, an increase in ankle plantar flexion. But then when you go from low intensity to higher intensity, we see that the knee flexion angle goes the opposite direction. So initially an increase of 8 degrees and then a drop of approximately 2 degrees. And this is something that we've seen in our research as well. If you look at Wendy's study from sports biomechanics, we can see that over a range of intensities from 60% of maximal heart rate to 80% of maximal heart rate and to 90% of maximal heart rate, we see a progressive change in ankle plantar flexion with a reduction in plantar flexion. So in other words, the ankle moves into a more dorsiflex position, and associated with that is a change in knee flexion angle. And if we look at the numbers, we can see that the ankle changes by approximately 6 degrees from 60% intensity to 90% intensity, and the knee changes from 37 degrees. So once again, about 7 or 8 degrees greater than the mid-range of the Holmes method, and then down to 34 degrees at 90%. So approximately 3-degree reduction in knee flexion angle at very high intensities. Well, what is driving this? Well, from that same data, we measured EMG activity, and this is the EMG activity at different quadrants. So this is the hip extension, knee extension phase, as well as the blue and green segments. And what we can see is that during that increase in intensity, to increase the workload, the force and the muscle activity applied from gluteus maximus increases progressively. And we see the same when it comes to vastus medialis obliquus and vastus lateralis, so the quadriceps muscles. And we see the same in other muscle groups, except for the medial gastrocs. And we see that the medial gastrocs are already at a high level of recruitment at 60% of maximal effort, through 80% and through 90%. And in fact, there's only a subtle increase in one quadrant, whereas in the other quadrants of activity, they are fairly static. And what is happening here is that as you're increasing the force applied by the gluteals and by the quadriceps, which are large muscles which can produce a high amount of force, the much relatively smaller gastrocnemius and soleus are unable to transfer that force effectively to the pedal, and therefore the ankle moves passively into a more dorsiflexed position where there is an increased tension in the muscle, which is then allowing it to apply that force through the foot, which is the lever that applies that force to the pedal. And that is responsible for that progressive move into dorsiflexion in the ankle. And that then results, because of the contact points not changing, the knee moving into progressively more extension, or less flexion, we should say. So if we look at a summation of those different research studies, and we look at Rodrigo's thesis, which was 2D kinematics, we see that we have a range of knee flexion angle of approximately 38 degrees, plus or minus 4.3, and that's at a low intensity. Remember, easily riding down the road. I didn't go over this, but Garcia Lopez measured differences between professional cyclists, 13 elite cyclists, and 14 club cyclists. The relative work, it wasn't a relative workload, it was an absolute workload of 200, 250, and 300 watts. And the average from 3 different trials was mixed into the kinematics. And we see that at a professional level, so this is a moderate workload, probably well below FTP for the professionals, and maybe at or above FTP for club level athletes. We see that professional athletes have a lower range of knee flexion compared to elite and club riders. So we see this difference between different levels of cyclists. In Wendy's study on 19 well-trained cyclists using 3D Vicon, the intensity was 70% of peak power output, or maximal aerobic power. And there we have a range of 35.5 degrees plus or minus 6.6. And then in that study, which I covered in the previous slides, we had 17 well-trained cyclists at 60, 80, and 90% of maximal heart rate. And the means for knee flexion angle at 60, 80, and 90 are 37, 35, and 34 degrees. So how do we put all of this together to understand what a reference range should look like ideally? And sorry, if we look at, and this is purely for dynamic kinematics, at bottom dead center position, we see that generally for low intensity activity, a range of somewhere between 33 and 43 degrees is where we would expect to find most individuals. At 90 to 100% of functional threshold power, and so I've actually looked at the results and how they relate to FTP, and that's a term that most cyclists these days understand easily. We see that the range is generally between 30 and 40 degrees. And that's an easy one to remember, 25 to 35 for static and 30 to 40 for dynamic. And it's also a workload that cyclists are comfortable doing in a laboratory. Once you get above FTP, they can't sustain it, they become very sweaty, and particularly with 3D kinematics, all the markers fall off. So we generally ask them to come up to a workload of approximately 90% of FTP, and then we do kinematic measurements at that. And if we look at maximal aerobic power, then we see that the range is approximately 28 to 38. And within these ranges, we know that elite cyclists will trend to the left-hand side and more recreational cyclists to the right-hand side. And there are various reasons for that. And a fundamental one, which is important, is hamstring flexibility. And obviously, the more aggressive the position, that hamstring flexibility will inhibit the knee flexion from reaching a minimum during the bottom dead center position. So those are the ranges that we would be able to infer from the research. So that's really the knee joint, which we've got a fair amount of data on. What about the hip joint? I mean, this is actually the biggest joint involved in cycling, has the largest amount of muscle mass, and contributes arguably at least 50% of the power produced during cycling. Well, what do we know about the hip joint? Well, first of all, if you measure kinematics in the hip joint, this is not a hip flexion angle. And we see this, unfortunately, in a lot of the research that has been published to date. And it is completely invalid. It has nothing to do with the hip joint. Similarly, if we look at 2D kinematics, this angle here is not your hip flexion angle, and also is relatively meaningless. And if you're using that in practice, is also almost completely meaningless. And we see that in various different software packages for 2D kinematics, but we also see this exact same angle being measured in 3D kinematic packages that are available for bike fit practitioners. And that is not your hip flexion angle. This is an oversimplified model. And here we have the different segments that are used to make up the shoulder flexion angle and the hip flexion angle in many of the 2D kinematic software packages and models, and also in 3D commercially available packages. And the problem is that this is not how the body functions. In this hip joint and shoulder joint, and between them, in this segment connecting those two important measurements, there are a total of 19 joints. And those joints are in variable positions of flexion or extension and result in different positions when measured accurately. And one way to measure them more accurately is to have at least 3 segments, but preferably more, and using a segment which corresponds to the position of the pelvis to measure the hip flexion angle, and a segment that corresponds to the upper thoracic spine on which the scapula lies to measure shoulder flexion angle. And even then, that's a much oversimplified model to measure shoulder flexion and may not be entirely appropriate in terms of its validity. One way that we can measure hip flexion angle is by using a goniometer. This is difficult because you can see over the greater trochanter, the arm of the goniometer is a long way from the sacrum, which is where you're trying to ascertain what position the pelvis is in. And so using an inclinometer makes that a lot more easy. And we've seen that that's accurate, but is it a really valid reflection of what the pelvis is doing when the person is cycling? We've seen how it changes with workload for the knee, but what about the pelvis? Well, a very accurate way is to use the 3D kinematics of the Vicon system. And as I've said, they use a number of markers, and that makes the accuracy greater and the validity greater, but it's a very expensive, aversive way to measure kinematics and not a practical method from a daily bike fit perspective. If we look at what data we have, we look at Wendy's study on the goniometer, the inclinometer, and 3D Vicon, we see that once again, we get very different values for each of these different measurements. And similarly for 3D Vicon, depending on the plug-in gate model that you're using, you get different values. And that's because the markers are being used in a different way. If we look at inclinometer-based data in Wendy's recently published studies on 50 well-trained cyclists, we see that on average, the hip flexion angle, and this is the minimum hip flexion angle at top dead center, which is where we run into problems because we're reaching the limits of hip flexion, and so that's where we measure it. We see a value of 77 degrees plus or minus 5, and we have data which we will be publishing in the next couple of months on world tour cyclists measured in exactly the same way. And lo and behold, we find a value that is well within the typical error of measurement. So 0.4 of a degree difference between 50 well-trained cyclists and world tour cyclists. So they adopt a very similar pelvic position. How do we measure those using our commercially available packages? Well, some of them can possibly, and some of them simply cannot. If we look at the retool package, we see that they only have markers on the arm, and this one is on the acromion, and then we have markers on the lower limb, and this one is on the greater trochanter, and there's a hip flexion angle that is measured, but as I've already said to you, that is completely invalid. There are no spine markers, there are no markers on the pelvis, and therefore you cannot do any hip joint kinematics, and you cannot do any shoulder joint kinematics. What about other systems that are available? Well, we know about, this is one that's not used very widely, but is a system that's been around for a while, bi-eraser motion, which uses light emitting markers instead of reflective markers. Well, they in fact have form like Vicon, have 4 markers on the pelvis, on the aces and pieces, and they have markers over the greater trochanter. So actually the same number of markers as the Vicon system. And so they can actually measure hip flexion angle, but then no markers on the rest of the spine. And so shoulder flexion remains difficult to measure or not possible to measure using bi-eraser motion. But this is a good way to measure the hip flexion angle and could be very useful. We need to obviously have a reference range for whatever they are using to interpolate that data, and whether they use a segment through those markers or like Vicon create a perpendicular, we don't know, and I don't have that data, but it could well give good quality data for hip flexion. And then we have STT, which is used by a number of fitters, and STT actually has 4 markers on the spine, right away from the C7 down to on the sacrum, and therefore can actually create a number of segments. Interestingly enough, the existing software package does not use these and uses a simple segment, an oversimplified segment from the greater trochanter through the acromion marker to measure hip flexion angle and shoulder flexion, and therefore doesn't give out data that is valid for those joints. We asked STT if they could please change their marker position and update their software. And to their credit, they were good enough to actually do that and had a turnaround time that was actually very fast. And we are now using a beta version of their software that incorporates a different marker set. And what we've done is we've placed the marker on L2 and then the center of the sacral promontory, and then on the upper spine on C7 and T7. And that allows us to get a much more accurate representation of the hip flexion angle, and hopefully in time, once we can understand the shoulder movements much better. And this is unpublished data, but if you look at the relationship between inclinometer measures and active cycling measures from STT using those markers, which very closely resemble the segments that we're using in the inclinometer, you can see that there is a very tight relationship between the two. And so what we see from this is that statically measured hip flexion angles and dynamically measured hip flexion angles when using the the marker set that we are at the moment are extremely well correlated and actually reflect the same thing. What do we know about the hip and how its function changes in cycling at different positions? We know very little, and this is an area that we ourselves hope to investigate in the coming years, but also that I think many researchers should investigate. I mean, the only really good quality data comes from Dan Hale's study in 1997. So we're talking 25 years ago almost, where he showed that your freely chosen hip flexion angle versus if they used 3 different C-tube angles and 3 different torso angles and created basically the scatter of different hip flexion angles. And what they saw is as you move away from your freely chosen position, there is an increased oxygen cost. So either cyclists develop an efficiency at their specific hip flexion angle, or there is an optimal hip flexion angle that is appropriate for economy and power in cycling. And probably it's a mix of the two, because we see that most cyclists adopt a very similar hip flexion angle, irrespective of their bike position and irrespective of what you do with the handlebar. And you saw that in the data from Wendy's study and from the data that we haven't published from World Tour cyclists, that they have almost identical hip flexion ranges, and they tend to hold those quite aggressively. What about the shoulder? Well, as I said, the shoulder is a tricky one, and we see that these measurements that we take using different methods come up with different results. And in fact, when we try to simplify it with STT, by moving this marker into a central position over the humeral head, in the position that the person adopts on the bike, we don't see any improvement in terms of the relationship between static inclinometer or goniometer-based measurements and 3D kinematics. And so that has to do, obviously, with the movement of these markers out of the planes, but also how systems are actually measuring those angles. And we are still busy trying to understand them. And for that reason, and because of its reliability and its accuracy, I feel that using an inclinometer is still a good way to, and doing that in a static fashion, is a good way to measure shoulder flexion. And if we look at that data, we're looking here, where we see a shoulder flexion of about 111 degrees plus or minus 8. This is 3D Vicon data. Here we have inclinometer data 112 plus or minus 4. And once again, from our World Tour data set, we see that we have a very similar shoulder flexion angle as well-trained cyclists. So shoulder flexion seems to also gravitate to a particular value and varies very little. And that is once again within the margin of error between a group of well-trained cyclists and World Tour cyclists, and can be measured statically using an inclinometer and can be used to define reference ranges. What about the whole body? So if we put all these joints together, what's happening to all of those segments at different intensities while we're cycling? Rodrigo published recently a study, I think this was last year or the year before, looking at internal external rotation and torso rotation and pelvic inclination and movements of these various different segments or systems during 65, 75, 85, and 95% of peak power output. And what Rodrigo demonstrated was that there were variable movements and also a difference between competitive and recreational cyclists in the degree of movement in these different planes. So that's one study that gives us some indication of what's happening. Wendy's own study, which I've already referred to, looked at how those different joints moved. What we see over 60, 80, and 90% is that the hip joint does not change position. So cyclists maintain the same hip flexion angle throughout their different range of activities. But what we do see is that they increase lumbar flexion. So you become more flexed at your lumbar spine. You have increased thoracic lean. In other words, the torso is more horizontal as you move to a greater intensity. The shoulder joint also remains in the same flexion range and doesn't change. And so that gives us a nice understanding that the static measures, even though they measure in a different way, are valid across a range of intensities and are not affected by the intensity at all. And then the elbow, where we see the greatest change, where there is a vast increase throughout the range of intensities with greater flexion of the elbow. And if you look at the picture, you can understand what happens. And effectively from lower intensity, 60% of maximal heart rate through to 90%, we see this progressively flexed posture of the lumbar spine and flexion of the elbow, while the shoulder joint actually remains in the same angle and the hip joint remains in the same angle. And so we hypothesize that this is to stabilize the torso so that you can transfer power to the pedal through the increased forces that are being applied across the hip and across the knee. So this may be a mechanism to stabilize the body. That would be the most rational explanation. One thing that also happens as part of this change from this position to this position is that the person slides forward on the saddle. And we collected saddle pressure mapping data and I published this as well, which shows that the individual moves forward on the saddle as part of that movement pattern. And this is well known by professional and recreational cyclists for a long time. Saddles used to have a leather cover with a rivet in the front to hold the leather down. And so when cyclists were riding at a very high intensity, they spoke about riding on the rivet. And that is exactly what they do. They slide forward on the saddle and they adopt this more flexed posture to stabilize the body. So in summary, static kinematics are accurate, reliable, and they're valid. But static kinematics are not sexy and they are not cool. And that is not great for customers. And that is why dynamic kinematics are used more and more frequently. But dynamic kinematics are also accurate. They are also reliable. They may be in some circumstances more valid because of the changes that occur at different intensities, and they are very cool. And so they are easily sellable. But importantly, dynamic kinematics are dependent on the workload. And certain areas such as the shoulder and the hip are not adequately researched at this time. And they require also at a commercial level in bike fitting, the correct marker set and the correct anatomical model. Using an oversimplified model with the segments that I showed for the hip and shoulder joint are not valid. And if you cannot adopt an appropriate marker set, an anatomical model and associated software, then you should rely on static kinematics to measure the hip and shoulder joint and use a combination of tools that you know and understand to measure those different joints accurately and reliably and validly. In the knee, as we already covered, the static knee flexion angle can be between 20 and 30 degrees. Sorry, that should be 25 and 35 degrees. My mistake, that's a misprint. And that's the Holmes method. And then for low intensity dynamic activity, 33 to 43, 30 to 44, what we mostly use in our lab and is an appropriate, I think, workload to measure knee flexion angles, and at maximal aerobic power, 28 to 38 degrees. With a hip, we see generally a range between 72 and 83 degrees. And this is for the majority of cycling disciplines. We do see that in the time trial position, that this lower range starts to drop to as low as 67 degrees. Once you get below that, you are reaching the limits of hip flexion, and is one of the reasons why many cyclists decompensate in an aggressive time trial position, when you can actually measure that quite readily using static kinematics. We augment that, especially in time trial positions, with dynamic kinematics, because the athlete slides forward on the saddle dynamically, and that's because they can feel that they are approximating the limits of their both hamstring flexibility and hip flexion angle. And so we measure both knee flexion angle and hip flexion angle dynamically to see how that changes. Vicon, when using the standard plug-in gait model, has a range of about 116 to 128 degrees. And using this beta version of the STT system, which we see is the same as the static measurements, we use therefore the same range. So easy to remember, 72 to 83 degrees. And we'll publish data on that probably in the next year and a half once we've collected a large enough data set and can share that with you. The shoulder, as I said, I prefer to use static measurements, and we see there a range of approximately 105 to 119 degrees. And we see this also in mountain biking, marathon, cross country, and gravel bike riding, which is increasingly popular these days. They're going closer to the lower range. And in world tour level cyclists and very aggressive positions, we see up to this sort of higher range of close to 120 degrees. Dynamically, you can measure shoulder flexion with Vicon, and there we see a 94 to 114 degree range. but using other systems, because they have less markers and because the interpretation of the different segments is not clear, I would say we need to be wary of using them, and we can confirm at a later stage what we are actually measuring there and how we should interpret that. Lastly, if you're doing high intensity exercise and you want to know what's happening there, remember that compared to low intensity exercise, the knee flexion angle will decrease by approximately 5 degrees, and plantar flexion will decrease as well by approximately 6 degrees. The thoracic area will increase its lean by approximately 4 degrees. Elbow flexion will increase the most by approximately 12 degrees, but very handily, hip flexion angle and shoulder flexion angle will not change at all from low intensities through to high intensity activity. So that really is just scratching the surface of kinematics, and hopefully increases your field of understanding of what we're measuring. And hopefully in due course, we'll be able to find a lot more interesting and relevant data that will help guide us in terms of being able to apply this to the sport of cycling.
Wonderful, thanks, Jeroen. I think it was really, really nice, and it was great to see a good summary of a lot that has happened there. As you said, some things have been on the radar for longer, and other things haven't been explored sufficiently. In terms of questions from the audience, we've got just one at this stage coming from Brut. He's asking whether you have experimented with linear regressions along the line, particularly trying just to assess whether a simplified hip joint sort of model would actually provide you some similarities with a more appropriate anatomical model, if you like.
So I think he posted his question before I gave the slide of our unpublished data on the STT systems beta version that we're using. And so to answer that question, yes, we have. And the correlations are really, really good for the hip, and the correlations are really, really poor for the shoulder. So hip joint, we're very happy with the data that we're collecting, and we'll publish the whole data set. We want to get approximately 100 subjects data, so that we've got a large data set and can get some really good quality data out of that. But for now, things are looking very, very good. And if any of you use the STT system, you can perhaps approach them and ask them whether you can have your software updated to the system that we're using and change those markers. There are 2 markers in the middle of the spine. It just means moving the upper marker up to T7 and moving the lower marker down to the L2 level. And then the rest is pretty straightforward. It's a plugin, and then you can access that data in the same way that you do on the system, only in the graphs. On the right, on the dashboard where it gives the hip and shoulder flexion, still interprets data in the previous model. But when you pull up the graphs, you can actually click on the new models that we are using.
Thanks for that. Let's see, I don't think we have any other questions coming just yet. I've got one, probably trying to get a sense from, in terms of your experience, do you think, and following up from what Barut actually just asked, do you feel it would be easier for practitioners, particularly that are using, let's say we've got someone in the clinic using a 2D system, trying to measure those angles, would it be better for them to try to upscale their model using markers on the pelvis to properly measure their hip joint, or should we try to develop that equation that would potentially provide similar outcomes, but with a simplified model?
Yeah, for 2D kinematics, it's very difficult. We in fact tried this as well. The problem is that the reference points that you want are very difficult to see in a sagittal plane. And so it makes it almost impossible to measure the hip flexion and shoulder flexion in 2D kinematics. And so really the only way is to do it either statically or to do it using 3D kinematics. And so that unfortunately confounds that. So my advice in that situation, and this is what we use in our daily practice, is to mix static and dynamic kinematics. What we do is we start with intrinsic measurements like everybody does. We apply those using algorithms that we've got in a commercial package. Then we look at the static kinematics, we look at the reference ranges, and we see any gross abnormalities. Then once we've corrected those, then we look at the dynamic kinematics that we understand. And that's predominantly the knee, and then also obviously movement of the pelvis and torso that we can obviously measure with both 2D and 3D kinematics, particularly coronal plane kinematics of the knee and so forth. And now more recently using the STT update to measure hip flexion angle. And we still measure the shoulder flexion using the inclinometer, and will do until we understand those better. I see. Yeah, you're welcome to. You can read the question and I'll answer. Sorry.
Yeah, no, sorry, I've got three coming through. One is around the LIOMO system for hip flexion. Have you had any experience with something along, not necessarily LIOMO, but more IMU-based systems?
Yes, so those are very promising units, and they give us some very cool data with regards to what's happening in the field, and you can use them in the lab and actively outside. And the LIOMO system is very good at measuring changes in the inclination of the pelvis, and obviously that in that way changes in the hip flexion angle. And we do use the LIOMO system from time to time. However, there isn't an ability to get an absolute in terms of the hip flexion angle, because there's no calibration process in terms of the LIOMO in terms of the position of those joints. So it's good for looking at changes during activity, but it doesn't give you anything in terms of a reference value to be able to apply to that.
So the other one is around if the knee flexion is decreasing when moving into a more high intensity effort, do you believe this is correlated to a change in cadence?
Yeah, indirectly it is, because at higher cadences, you're using lower forces. So it's more a force related factor. So if you do low cadence and at a relatively low workload efforts, you have high levels of torque. So I would say an accurate way to correlate the knee flexion angle and intensity would actually be through measuring torque. And you can do that on actually, for instance, the standard Wahoo unit has that as a metric that you can see. And we can do that also with Garmin with a simple little plugin that you can do through Garmin Connect. And so it's more than likely related to the torque value. And that is obviously determined by the workload and the cadence. So there is a relationship between those.
Yeah. So the other one is from Ina. She's asking, obviously thanking for the presentation and asking whether you think we need to move towards bike fitting methods that are collected outside of the lab.
Yes and no. The lab is a very controlled environment and allows us to standardize things, but we know that your movement pattern on the bike is not this in a stationary manner that it is when you're sitting on your typical ergometer, which is holding the bike vertically. And so movement patterns outside in the field are a much better reflection of reality, but it makes data collection very difficult. We do that in the velodrome. So a velodrome is a good place to collect data, and we do that for time trial fitting because it's a very much more valid place to look at how those kinematics change. And it's difficult, obviously, to measure the actual joint angles. So LIOMO and saddle pressure mapping together with aerodynamic aids are what we use in a velodrome situation. And hopefully in time, we'll be able to measure kinematics as well out in the field. But at the moment, there are no systems that allow us to do that. But it certainly would be a more valid way to measure the body's movements because of the natural way that we cycle.
Yes, yeah. That would be a nice one where we have the opportunity to actually measure those on the field. Another one, and I think probably comes along with the prior question around the IMU. If you had some experience on there, what your thoughts are, and
Yeah, so we actually have we've used full body IMU systems in our lab and tried to see whether we could apply them to cycling kinematics. The problem with those IMU units is that they do have drift, and so in the first few seconds of data collection, if you use, they have a particular sort of almost a calibration pose to get the IMU systems to understand where each unit is in space. But as soon as you start using them, they start to drift. And we do see that over a period of time, the drift just gets progressively worse and affects the data collection. And so that has been a limitation with full body IMU systems. And for that reason, we didn't pursue that. because it's very difficult to correct for that in the field and dynamically during a session where you're collecting data. So hopefully in time, they'll overcome those limitations with a mix of IMU and either markerless or marker-based kinematic systems. And if they can integrate those two, that will probably give us some very useful data that IMUs can then add to the equation.
Another one that has come through is around the 90% FTP intensity, because even leisure cyclists will spend majority of their time on the bike at much lower intensity. So really the relationship between the intensities that you've mentioned with lower intensity cycling, what your thoughts are on that?
It's a good question, and we do, just simply because we like to standardize things, and having a bunch of different ways to do something starts to complicate the picture. We realize that there's a linear relationship between the different intensities. And so if we use a particular reference range for the fitting, and it happens to be 90% of FTP, if the cyclist spends the majority of time at a lower intensity, the reference range is still appropriate, because we know that what we achieve in that intensity will be, and for instance, we know that the hip flexion angle, shoulder flexion angle won't change. We know that the knee flexion angle will be in an appropriate space. And we know that if they reduce their intensity, they'll probably shift a little bit back on the saddle and have greater engagement with the saddle when we use saddle pressure mapping and so forth. But it's an important and good question. The world is not ideal, so if we could do everything for everyone perfectly, we would, but that makes life incredibly difficult and complicated. So the answer is no, we don't.
All right, thanks for that. Let's see, I don't think we've got any other questions just yet. Probably I might call it to a close. Before we actually finish, thanks again, Jeroen, for your presentation. It was really, really nice. And I think it comes along through very nicely from the talk that we have from Gitan. He concentrated on the forces, and now we have a very nice description of the movement. So I think sort of those two things actually come together very well. Oh, sorry, there's another one just coming through. How often do you advise rechecking feet? What factors you consider injury fitness and all of that?
Thanks, Nikita. It depends on the individual. So if it's for instance, a elite or professional athlete who hasn't got any significant change in their training load, they've been riding for a long period of time, assessing their fit can be, as infrequent as once a season. If you've got somebody who's new to the sport, who's undergoing numerous neuromuscular changes, then we can tell them to come back in a shorter space as 4 or 5 weeks. Same if we pick up a particular intrinsic factor. So if we see that in an individual, hamstring flexibility is a very limiting factor, and we ask them to start stretching and want to see how that changes, then we'd ask them to come back in 4 to 6 weeks and have a reassessment. So it's really dependent on the individual, but the one big factor is how their load is changing. So if they're new to the sport and they're actively increasing their training, then they need to be reassessed much more frequently.
Thanks for that. Yeah, I think I'll probably finish up then. Thanks again, and just keep an eye, everybody, please keep an eye on the upcoming sessions. Ina is doing a lot of work for us trying to manage our Twitter Cycling Research Network account now, so we should see those sessions coming through once we have confirmation of dates and all of that. But thanks again for everybody that logged in today, and hopefully see you shortly.
Thank you, guys, and thanks everybody for coming to the talk.